Okay, let's start again. I suppose you can hear me from afar. If not, leave a chat message. And let's move on. So second session is supposed to be unsupervised learning. I'm checking because I don't remember. Okay, so we have two notebooks for unsupervised learning, and we have the slides as well. No, not new share. Okay, I guess you can see the slides in your broadcast. Unsupervised learning. So we have principal component analysis and this T-distributed stochastic neighbor embedding. Right, so let's get to it. All right, let's start with PCA. I don't know if you're familiar with PCA, but this notebook assumes you are not. So it's gonna get to the core of it. No audio? Okay, so everything should be fine with the broadcast. I'll move this a little bit closer. All right, it works there. Awesome. All right, so principal component analysis. Sometimes you have a huge, it's unsupervised learning. What the goal of this is dimensional action, make it easier for us to find patterns in the data. Imagine that you have a huge amount of data and it's high dimensional. So a piece of data that would be a descriptor for a system, for example, is made of these many components. So if you have a database of them, you can build this kind of matrix where you put on the rows your descriptors. So far, so good. We want to basically transform this matrix. So it's a rotational space. It's a change of basis, if you like. We want to try to maximize the variance in the data. So as such, it may be difficult to find out, but there may be a direction in the dimensional space along which the data has the highest variance. So it's very spread. We want to find that. That's the goal of this. So we want to find this transformation, and we can do it following this procedure. So we have to calculate the covariance matrix of our data. And yeah, and this would give us this X, and then we have the transformation right at hand. This doesn't look very complicated, and it's actually not for once. All right, so let's try. We initialize some stuff, and here is all that you have to know about the PCA function. So the first function, we are using the NumPy package for linear algebra and matrix handling, so it's all easy. You don't have to write your own covariance matrix function. You can use the one from NumPy. So first we calculate the covariance matrix of the original input matrix X. Then we diagonalize it. We need to find the eigenvalues, eigenvectors. The eigenvectors would give us the coefficients, if you will, the components are the coefficients of the linear combination of the original directions that would give us the new direction. And the eigenvalues normalized would give us the variance of the data along that direction. So let's compile this function. After that, all we do is just apply the transformation once we have the eigenvectors. And the function will return the transformation matrix, the transformed data, and the eigenvalues so that we can check the variance. Now we have some toy data. This is just a z-score function which is used to normalize data. If you have some features in your descriptor that have very big values and some others are very small values, clearly there's going to be more variance in that particular axis. Right? Imagine that your database is a database of countries, and the first column is population, and the second column is GDP. The third column is percentages of the surface that is water. Clearly, the percentages are always going to be between 0 and 100, but population is going to be in the millions, and GDP might be in the billions. So the data is biased. Clearly, there's more variance in the GDP, but this is artificial. It's just because GDP is a big number to begin with. The Z-score is kind of renormalizing your data by the standard deviation and shifting it around the mean. So shift around the mean, rescale it so that all the numbers are between, let's say, -1 and 1. Not really, but they're all on that kind of range. So every variance you will see in the data after applying the Z-score, you can kind of believe it's there. So compile the function. Great. Now we create some toy data. We have the original and the Z-score data. The original is this, it's an ellipse. So it's two-dimensional data, just to make it simple for us now to toy with. It's an ellipse, and you notice that it's translated and rotated. So the axis of the highest variance would be this diagonal axis of the ellipse, but it's not visible yet. It's diagonal. Now, after applying the Z-score, you see that there is a normalization, so the size changes, and also now it's shifted around the mean, so that the ellipse is centered roughly around the origin. Great. Then we apply the PCA, and we get two eigenvalues. There's two dimensions, so we get two eigenvalues. One is clearly a lot bigger than the other, because the ellipse is asymmetric. It has a major axis and a minor axis. There is more variance along the major axis, and that's what this means. So if we look at the transformed data now, the Z-score data is the blue one, and the transformed is red. And now you see that the ellipse got rotated. And the x-axis is the first principal component with the highest variance, and the second axis is along the minor axis of the ellipse. Very simple conceptually. Now you extend it to 100 dimensions, and this will still work, but you will get 100 axes. So what do? You prune away the axis with small variance. You keep only the axes that have highest variance. You can keep 2, 3, and then you can make a representation of your data. If you would keep more, then it becomes more troublesome to make a plot. But this could be a very quick tool for checking if your data is organized in some way. So there is an exercise which I think we can go through quickly. We have a database of wine, because I'm Italian. So we have chemical descriptor of the wine, alcohol, malic acid. So these describe the content of the wine. We have 13 of them. They're quite chemically sound. Yeah, great. So we can load. The data is stored in your notebooks inside this data folder. We have the inputs, and we also have the outputs. The outputs are classification, whether the wine is good or cheap. No, sorry, good or bad. We have high quality, medium quality, and low quality wine. 1, 2, and 3. But in principle, we do not need the output. This is unsupervised learning. We just look at the inputs. We try to find if the input cluster up. So if wine that is labeled as good will all end up in the same area of space. We could do something like that. So if we execute this one, of course, nothing really will happen because we have to apply the normalization. So we have data in. Let's start by looking at what data in is. A matrix. Every row is one wine, and every column is one descriptor of the wine. So, okay, we have it. We have to apply the normalization. So we would like to do the Z-score, just because we are not sure all these chemical parameters live in the same range. So let's go like this. Let's copy paste. Let's be lazy. Now X would be z-score of data in. And let's print it again. Print x. Seems like nothing much changed. But yes, some number perhaps did change. You should always apply it when you're not sure, because there may be some, if you have a really large database of gigabytes, you're not going to be able to look at it like we are doing now. So just be safe and do it. Then we're going to apply the PCA transformation. Easy, we copy it again. So yeah, the input matrix is X, and then we will get this stuff out. Let's see. I can remove these prints. I don't need to see the data anymore. Right, now we get the eigenvalues. So clearly there is a direction with a lot of variance. So let's say the first two directions contain a lot of variance of the data, and the others gradually less and less. These are sorted automatically by NumPy, so that's why they become smaller and smaller. Here we see the normalized cumulative sum of the eigenvalues. So we see that if we would keep 4 components, we have roughly 75% of the information content still at hand. If we would keep 12 components, then it gets more than 95%. But the point of this is to remove dimensions, and we want to remove the dimensions that are less important. So just for the sake, we can make a 2D plot. We know whether we're going to keep about 55% if we have 2 dimensions. We are throwing away a lot, but we can show it. Now let's see. By the way, this is an exercise. You should do it yourself. We have the transform data. This is YPCA. Now I'm asking the system to give me every row of this matrix, so every wine, but we only want 0 and 1 component, so the first and the second component. There they are. And we can perhaps make a plot of these things. Mm-hmm. So in this plot function, we would have to put the X values and the Y values. So first the X, and that would be component 0. And for a Y, we want component 1. We don't need to show this one anymore. And now we have it. So you can maybe, if you squint enough, you see there are kind of groups of points. Perhaps these do correspond really to the good, medium, and low quality wine. But it's not so clear. The reason why it's not so clear is that, well, we threw away 45% of the information content by killing those components. So perhaps we threw away too much. Now, if you want to do this exercise later, you can try to color the points. So this B means blue, but you can make a plot by coloring the points by their true quality. So if you look at when we loaded the data, we also have data out. Now, data out is an array of 1s, 2s, and 3. It will tell you the quality of the wine. So you could pick all the wines that have 1 and make a plot with them with, let's say, blue color, then all the ones that have 2, and this would become the medium, and then the high quality ones, number 3. So you can separate the points and give them color, and you see where they end up being in this 2-dimensional space. That would be left for you to try. Any questions about PCA? Yeah. Okay, so is there a systematic way to determine how many components to keep? No, there isn't. In this, we just wanted to make a simple plot, so we throw away everything but the first two. If you're trying to optimize a descriptor, you might still have to test. So you have the full descriptor, you apply PCA, and then you start pruning. This will make your descriptor simpler, but is also throwing away some information. And then you have to check, is the learning stable? Is the learning still good after I throw away 1, 2, 3, 4, 5? So you have to find your own compromise there. The only systematic way is testing. More questions? Is it clear?
Can you increase the font size?
Can try. Enough? Yeah, so this is the part I wrote. Let me maybe remove the, yeah. This is the part I edited, doing the Z-score. And PCA is also used in for analysis of molecular dynamics because you have a system that is vibrating. Let's say a big protein, and it's all shaky and wobbly in water. You might want to find what are the vibrational modes. So you can just take the trajectory and do PCA, and it will tell you, instead of the variance, well, it is still the variance, but the eigenvalues will basically give you the frequencies. And the eigenvectors will give you the vibrational modes. It's the same mathematical apparatus when you're doing vibrational analysis than this. No more questions? Then I can move on with our lives. Good. So the other one I wanted to show was the TSNE, T-distributed stochastic neighbor embedding. So fancy. Unfortunately, I really do not understand the mathematics of this, but this is not a bug, it's a feature. It shows you that you can use these tools as a black box without understanding really what goes in. Well, then you get crappy results and you kind of have to open the black box. But it's not going to happen today. If you want to know more about how this works, you can look at the Wikipedia page because that's where we all look. There probably are some papers too, but TLDR. Okay, let's try. This Python package, scikit-learn, has already all these functions in, and we are grateful for that. We don't have to implement our own. Right. Again, we use the wine. And now we are doing what you're supposed to do in the exercise for the PCA. We are kind of asking where are the wines classified as 1? Where are the ones classified as 2? So we get the indexes of those guys. We load the same data. If you're curious, we can print IDX1. This would be a list of indexes of wine labeled as 1. It's just a list of numbers. So now we know which points are labeled what. Then we just call the TSNE function. It's that easy. And make a plot. On this plot, we will just, we request the TSNE to be done with 2 components. We could put any number, but to make a simple plot, we just keep 2 components. And this is the data that will go in. Fit transform, and then apply the TSNE. It's very, very simple. You can check the manual of scikit-learn if you want more details about what these things do. Right. It seems we have 3 classes, 3 groups of points. Perhaps it worked better than PCA. So we don't know if they are grouped correctly, though. We would have to apply the coloring to each point and see what class is supposed to be. Remember, when you're doing unsupervised learning, you wouldn't have this information in principle. You just have the descriptor, the input, not the output. But now we are lucky we have it. And this is the result. So yeah, it kind of worked. We get 3 groups of points, and they are mostly of the same color. There is a little bit of noise, but if you think about that, we throw away a lot of information. We had 13 descriptors, and we are ending up only with two components, which the system decide what they are. There is a little bit of noise, but overall, we can tell the wines apart from the chemical composition. So sommeliers are not real bullshitting you. There can be some science behind it, wine tasting. This also means that if you get the chemical composition of a new wine that is not in the database, you can just apply the transform and see where it would fit. Even not knowing what red, green, and blue really are, in principle, you could do it. Questions?
I have a question. Your PCA result, how does this kind of clustering expect any similarities, or if we get any, it's purely accidental?
I have no idea, because I don't know the mathematics of TS&E. I would say it's a different way of transforming your data. So it's, yes, but how does it decide which one are larger? The formula may not be just this linear transform, it may be different, and that's why. It's the same when you're doing clustering. You have to feed a function that quantifies the dissimilarity, the distance function. Depending what you put in, the results are affected. So I would guess it's the same thing. The algorithm is different, the formula is different, and you get something different. Yeah, now you can quality check it because you have the correct labeling, so you can do it. If you don't have the correct labeling, then it's just something, right? There are some exercises.
So it works by defining 2 different distributions. It's going to minimize the k divergence. So that's kind of a measure similarity.
And how is this different from the PCA?
Well, it uses an optimization algorithm. So it doesn't just pick that like that. So that's a similar thing.
Thanks for looking at Wiki. Yep.
We also note that PCA is based on covariant, which is trying to find the linear correlation between
I guess I should repeat it for. So luckily there are 2 people here who know more than me about it. And so it's in PCA is just a linear thing, right? The correlation matrix is just trying to find linear correlation between the features. And all that PCA does is trying to maximize the directions, trying to maximize the variance with respect to the direction of the axis. And it's all done linearly. But this TS&E is trying to optimize some distributions. So there is some nonlinearity, which better results, or at least different results. Right? We can never really say one is better than the other. It might depend on the data. I see no reason why those chemical descriptors should be linearly correlated to begin with. They are just chemical compositions of wines. So the fact that you have more alcohol or less alcohol should not be proportional to the amount of phenol or ash, so that may explain. So exercise, if you like this kind of iron stuff, we loaded a database of iron structures. They're clusters. They're not, I think they're not really real stable materials. They're just some random deformation of clusters. Anyway, the idea is to use a MBTR to get a descriptor for each. And of course, MBTR descriptor is going to be long. It's going to be lots of numbers. But we can prune it down with TSNE from thousands to 2. And then we can make a plot and see if it can distinguish the FCC from the BCC, face center cubic, body center cubic. These clusters have structures, which we can kind of quantify, but we will have to really look at them, and we are lazy. And if we have thousands of these structures, we don't really want to look at each one. So either we have an algorithm to decide which ones are BCC and which ones are FCC, or we use this black box and trying to cluster them to reduce the dimensionality of this descriptor and make a simple plot. So this is another direction you can explore. I would say it's a very interesting exercise. There's also some help. It sets up the MBTR for you. All you have to do is the plotting and coloring the plots. So, a question: is this really a good example for dimensionality reduction? It looks to me like a task for clustering. Well, I kind of spin the example towards clustering. But yeah, that's right. This is maybe not the best example for dimensionality reduction, but it's intuitive and visually intuitive to understand what's going on. You can apply this machinery to true dimensionality reduction when you get this descriptor and want to feed it to a neural network. This is what you would do. So this is the point of this exercise, is to get you familiarized with these tools. So someone asked if the answers of these exercises are published somewhere. No, they're not. It's research. There are no correct answers. Yes, there are, but you have to find them yourself. There's no end of the book where you can cheat. So yeah, anyway, for this morning session, I'm done with presenting the notebooks. So you can use this time to explore all the exercises of the previous session and these ones as well. If there is some topic that you want to learn a little bit more, I'm here, you can ask. I'm online too, and yeah, if you need help with anything, just ask.